So here's my last video of the morning for you, I hope. But if you haven't done this first page, super easy. Click, do this, you get your volt, you get your answers. And what you can start to see is what's breaking off and what's sticking together. And now that we've talked about galvanic and voltaic cells, we can think about the dissolving and the forming, and that starts to make some sense. Right here, if you haven't looked at this yet, what you're going to do is come right back up here, and we're going to be looking at the one that's magnesium and copper. And you can think about, or even go back to the simulation, what's losing electrons, what's gaining electrons, and figure out what's oxidized and what's reduced. You can do the same thing here with magnesium and silver, and even magnesium and hydrogen. So it's focusing on these guys and focusing on this one with the idea of defining what is the anode, what is the cathode, what's gaining and what's losing. And what you end up here is a balanced ionic equation. We have a half reaction for the anode, we have a half reaction for the cathode, but you're just showing which thing is starting as a metal, which thing's starting as an ion, and then which ones are ending as each in those cases. So that is very helpful look into, instead of just what's dissolving and where the electron's going, how does that turn into a reaction? Right here, we are just thinking about, once again, that when we're losing and gaining electrons at the cathode and at the anode, we are dissolving, or we are forming solid onto there. Right here is where a lot of people have been asking great questions, and it connects very, 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 very much to the difference between galvanic slash voltaic, sorry, and electrolytic cells. When we look at this, it says I am using magnesium metal. So right there, magnesium metal is what we have, and sodium ion is what we have. So we aren't just taking these two and trying to see how can I make it a positive voltage. We're recognizing that if I have sodium ion, the only thing a sodium ion can do is be reduced into sodium metal by gaining that electron, but that requires negative 2.7 volts. If I have magnesium metal, I can't reduce that any further. It has to go back the other way and be oxidized. So I have to flip this. I'm thinking about this. This has to be my cathode. This has to be my anode. And if I do the math on that, negative 2.7, because it's my cathode, minus negative 2.37, I end up with a negative voltage overall. A negative voltage overall means that when I put these together, it's just going to sit there unless I give them some voltage. So this is a case where this reaction would not occur. It's a lot like that first quiz question of, when I put this ion with this metal, it either reacts or doesn't, and it comes back to what's going to be oxidized or reduced more often. What you'll see here is that two of them do react, two of them don't react, and one of them is a little bit weird, and I'll leave that for you to figure out. But when we are talking about acids, that's when we're talking about H plus ions. So for the acid, it is H plus ion. And since the acid is the ion and not the gas, this guy has to be the reduction. When we come down here, we click, we do with this, we do that, we do this, we see mass changes. So what you're going to see there, this is your first look at an electrolytic cell. It's going to show you electrons still going anode to cathode. We're still thinking about a lot of those things, but this time we're actually bringing in the idea of current and time and what's happening to the atoms. So this will walk you through the increase, the decrease in mass, and the flow of electrons. Anode, cathode, all of that's the same. Down here, we are starting to do math. And this goes right along with the last problem that I skipped over, but told you to look at on the electrochemical essentials, or the notes, where it is one thing at a time. Okay, well, the current times the time. Current is coulombs per second. Time is how much time. So then that can tell me how many charge or how much coulombs there are. Right here, you're going to do a dimensional analysis or a stoichiometry problem. Well, I know that I have a certain number of coulombs. That's the answer from this. And then there's a certain number of moles per coulomb, or coulombs per mole, depending which way you want to define or think about that. So then I can think about how many moles of electrons there are. Then I come straight down here. Okay, well, I know that how many electrons or moles of electrons I have. Well, how many moles of electron reacted right there? And ultimately, we can then, once we are in that realm of moles and electrons, we can just do normal stoichiometry and think about how many grams that is. And hint, it's going to connect very, very much with what you're seeing up there. We're going to have to wait till Friday or Monday to do this. But what we're going to see is that batteries actually make chemistry happen in kind of a cool way. So that's our goal. So skip that, skip all of these because you don't have that yet. But you can come to this. This one right here is a galvanic cell. Again, it's a battery. It's a reaction we already did. Copper and silver. It's this, scroll, scroll, scroll. Right here. It is that same guy the first time you do it. But the difference is we start with 1 molar and 1 molar. We get a certain voltage. We figure out what's the cathode and what's the anode. But then we start messing with the voltage. We start putting higher and lower amounts of silver in, and we put higher and lower amounts of copper in. And what you're going to see is that changes the voltage. Just like a battery dies over time, when some of the chemicals run out, we run out of the thing providing or the thing gaining or the thing losing the electrons there. So it makes the voltage do different things. So initially, you're just going to see what the values do. But right here, it asks you to use an equation. That equation is called the Nernst equation. It can be used to do a calculation, but we will very rarely, oh, look at that beautiful cursive, do the actual calculation. That right there, I just put a number sign or a pound or a hashtag or whatever you want to call it there because it's like RT over FE or there's an N in there or something. That doesn't matter because we're not going to do the math. Right here is saying, well, my normal voltage. Normally, my voltage, I think, is 0.47 in this case. We're thinking about, well, why does my voltage go up or go down? It's not because of R, that's a constant. It's not because of temperature. The temperature is not making it go faster or slower or do whatever. It's not because of the number of electrons. It's not because of F. It's not because of any other number that we plop in there. It's because of Q, my ratio, equilibrium of products to reactants. In a standard cell, I have 1 molar and I have 1 molar. A standard cell is 1 molar over 1 molar. We may not be natural log masters because I'm not, unless I've recently studied it. But 1 over 1, we know that is 1, and the natural log of 1 is 0. So that means if I have 1 molar and 1 molar, E minus the natural log of 1 or minus 0 just means, yeah, I've got my standard voltage. But when my products go way, 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 way up, I'm now taking the natural log of a positive number or of a big number, which comes out positive. So when products goes up, that means natural log, I'm going to be subtracting something right here. Well, I had a voltage and I subtracted some. And from a explanation sense, if I have too much product, the forward reaction becomes less and less and less favorable. I already have my product. I don't want to make more product. So the voltage becomes less favorable and I get less voltage. The other way that can happen is if I keep this at 1, but my reactants go way down, like 0.001. I have almost no silver, for example. Well, now I don't have enough chemical to force the reaction forward, or the forward becomes less favorable because I don't have enough stuff. So I have some voltage, but I do my natural log, and then I'm subtracting some value away. My voltage gets smaller. The opposite, though, is what if I put in extra reactants? That gets pumped up. Awesome. I'm going to put in more chemical, more chemical, more chemical. And the reaction's going to become more and more and more and more favorable because I've got more stuff to react. Well, if I keep this as 1, but put a big number on the bottom, my fraction now becomes a fraction or a decimal. We may or may not know this, but the natural log of a decimal is a negative. So when I do that, I'm doing now a negative minus a negative. A negative and a negative is a positive. We don't care what the exact value is, but that's where we are bumping up and pumping up our voltage. I've got extra reactance from a conceptual sense. The forward reaction is becoming more favorable. When it becomes more favorable, my voltage gets bigger. Or if I didn't have more reactants, scribble, 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 but I took away some products, now my ratio of reactants to products isn't my standard ratio. So the cell tries to make more products. It becomes more favorable. Even though I don't have more reactants, that lack of products makes the forward reaction more favorable. Same idea. I could keep this as a 1, make that a decimal, a negative, and a negative becomes a positive. So, kind of like the G is delta H minus T delta S, we don't use this equation always to get a number. We often use this equation to get that concept. Am I bumping up my voltage by making my forward reaction more favorable and proving it in terms of Q and what that does to this equation, or am I making it less favorable? You can explain this just in terms of forward favorability based upon reactants and products, unless it asks for the Nernst equation. The Nernst equation is this equation, and sometimes we'll see that because for generations, people have been explaining this wrong in terms of equilibrium and in terms of other things. And this isn't truly an equilibrium. So one thing I'm going to do just really quickly, I don't want mouse, I want pen, I want to clear that. I'm going to come back and I'm going to scroll, scroll, scroll. I said people are explaining this in terms of equilibrium, and that's incorrect. So anyone who made it to the end of the video, I will tell you right now, this has a voltage of 0. This will not react because it's at equilibrium. It is just as likely for the potassium ion to turn into the atom as the atom to turn back in the ion. And we're like, that's cool. But guess what? When a battery dies, it's not dead. It is just at equilibrium. It is going back and forth at the same rate. It is doing reactants to products, products to reactants at the same rate. So our salt bridge is just kind of jiggling back and forth, if you will, and our electrons are just jiggling back and forth. We are no longer pushing them any one direction, so we can't get voltage out of it. That's a dead battery. Equilibrium is death in terms of a battery. And the reason we can recharge some batteries is that they're made to be reversed. An electrolytic cell is just pushing those electrons back, starting our equilibrium over. Or if we're going equilibrium, pouring all the water back into that first graduated cylinder so that we can transfer back over and back and over and back again. So a lot of talking from me, way more than if I was there, but also a lot of help to come back to later.